All right, we're backing up to do 2.2. I feel like it's helpful to know the power rule in order to make lesson 2.2 a little bit easier. So I usually teach those in a reverse order. We're going to learn the concept of differentiability today and what that means. It has to do with the concept of a derivative. Okay, but differentiability is an adjective that describes the way the shape of a function goes. Okay, so we'll talk about what that means. We'll talk about its meaning. We'll talk about things that are one-sided. So last chapter we were doing one-sided limits. This time we're going to be doing one-sided derivatives. We'll talk about differentiability and when it succeeds and when it fails, the test for differentiability. So we have vertical line tests for when a function passes or fails. So we have a differentiability test too. That'll be when a function passes or fails it, and what the implications are for that when it does pass. Okay? All right, so remember, when we were working on limits, that we were checking limits from both sides. So when I say check the one-sided limits, you were doing the limit as x approaches some number from the left, and it's important for you to put then f of x after that, or g of x, or whatever function you're working on. And then on the other side, we would put x on the plus side, or the x on the positive side. Okay, now when you want to write to another mathematician that this is something that you are investigating, okay, so somebody's looking at your work, then what you would do is above the equal sign, you put a little question mark. That means you're investigating whether or not those two things are equal or not. Okay, so this is, you're maturing in your mathematical notation and learning how to write good math. That would be a symbol that somebody else would read and understand. Okay, in the same way, we would check one-sided derivatives as well. So we would check the limit as a approaches from the left, and this time you're going to put f prime, and you're going to investigate whether or not that is equal to the derivative on the other side. And again, you're going to put a question mark. Okay, when you're investigating the let me back up. When you're investigating the limits, yeah.
With that limit as x approaches a,
Oops.
prime.
Yeah. When you're investigating limits, you're checking the y values on either side. Okay, the y value on a minus, the y value on a plus. If they're the same, then we have a limit. Okay, what are you investigating when you're checking f prime? The slope value. Okay, is the slope value on this side the same as the slope value on the other side? Okay, imagine a parabola for me. Okay, maybe an upside down parabola. Can you picture that in your mind like this? Okay, if you sit on the top of that parabola and you look to your left and you look to your right, are the slopes on either side the same? One slope is what type of number? Negative, and the other slope is positive, and you look on either side and those two things are not the same. Okay, so that's what we're looking at here to define, we're investigating whether or not it happens. Okay, another thing that you might see advanced mathematicians do is after they're done investigating, okay, then the equal sign would come off, and either one of two things. Either they're not equal, and I think you guys know how to show that, right? How do you show two things are not equal? Okay, you put a line through it. Okay, do you know how to show that two things are definitely equal and I have checked it and proved it? You add the third, and that is to say I have verified that those two things are equal. Okay, so as you're investigating, you might see some of that come up. Okay, now, if you did not know the power rule that I taught you yesterday, you would have to investigate your derivative using Leibniz's or Newton's notation. Okay, so you'd have to do all the a plus h and the x approaching h and all h approaching 0 and all of that. Okay, now that you know the power rule, I'm empowering you to use the power rule as you check. Okay, you don't have to go back and rely on Newton and Leibniz's definition. Okay, so just so we're clear on that, you are allowed to use the power rule going forward. Okay, so when you check your two limits, remember that not only, or after you check your two limits here, if you go on to check this next part, then what are you checking? Now you're checking continuity, okay? Because just checking the two limits doesn't mean that the little point is filled in the middle, okay? You are checking continuity as well. So check continuity also. When you have a situation where continuity passes the requirements, but differentiability fails the requirements, okay? So when the 3 requirements for continuity, left, right, and the closed dot are all equal, and you're like, yes, it's continuous, but when you move on and you check the slopes, and the slopes are not approaching equal values, okay, the word for that is non-differentiability. T-ability, okay, non-differentiability, or they are non-differentiable functions. They are continuous functions, but not differentiable functions or non-differentiable functions. So you can have continuity without having differentiability, okay? But the opposite is not true. If you have differentiability, you for sure also have to have continuity. Yeah.
What does it mean to like differential?
When the left-sided derivative and the right-sided derivative are the same. Okay, so we're going to get to that in just a second. Yes.
Just to repeat what you just
Uh-huh.
said. So you can have continuity without differentiability, but you can't have differentiability without continuity.
Correct.
Okay.
Correct.
Thank you.
Yes. Yes. Okay. So for example, show that this function is not differentiable. Okay, so let's just look here. We're looking at 0. This is the connection of what kind of a function is in quadrant 3, according to the equation? Cubic.
Yeah.
Connected to what kind of a function? Okay, a linear function, right? All right, so if you're sitting on 0 and you look to your left and you look to your right, all right, and you're sitting there in your little point in microscopic space, and you look to your left and you look to your right and you look to your left, and oh, I look to my left and my limit is 0. And I look to my right and my limit is 0. And then I look at myself and I'm on 0. Because if all those things are true, then what's true about me? I'm continuous, okay? Then I look to my left and I check the slope, and I look to my right and I check the slope, and I got to find out if those two things are the same. And if they are, then I'm differentiable, and if they're not, I'm non-differentiable. So let's check those things, okay? So that's graphically what's going on. Let's do it mathematically. So first, you always have to check continuity. All right, so we are checking the limit as x approaches 0 from the left. And on the left, we're using the cubic. And then we'll check the limit as x approaches 0 from the right. And on the right, we're using 4x. And at the end, we're going to check f of 0 itself and see what f of 0 is. And so above all these equal signs, you put a little question mark. I'm investigating, are all 3 of these things equal? All right, so what is the limit on the left? 0. What's the limit on the right? 0. And what is the function value at 0 using the equal to bar? 0. All right, so 0 equals 0 equals 0. All 3 things of those are equal, therefore I'm continuous. All right, so now I move on to the question of, am I differentiable or not? Okay, and so to figure out if I'm differentiable, I'll be checking the limit as x approaches 0 from the left, but I'm not using x cubed anymore. I'm using the derivative of x cubed,
3x squared.
which is 3x squared. And then I'm going to check the derivative on the right. And I'm not using the linear 4x anymore. I'm using what derivative value? 4. And I put a question mark there to investigate that. And so then we check what the limit value as x approaches 0 in 3x squared is. What will that turn out to be? 0. And then on the other side, I have a constant value of 4, so that's equal to 4. 0 and 4 are not equal to each other. Therefore, I am continuous as a function, but I am not differentiable as a function. Okay, I am continuous, but I'm not differentiable. So it's important here that you identify, what you're like, use the actual x cubed as the function and then change it to a derivative when you're ready to check the differential. And then use the 4x as the linear piece and then change it to its derivative when you're ready to check that side of the differential. Okay, so visibly you can look at it, but algebraically this is how you prove it. Okay, so the conclusion is continuous yes, differentiable no. Any questions on that? Great. Okay, most of the functions in calculus are differentiable functions, okay, on their domain where they're defined. Their graphs are unbroken, their graphs are smooth, the slope is well defined, okay? All of that would be a visual check for whether or not it is differentiable or not. But what's the opposite of being unbroken? Broken. If you encounter something broken, how could a graph be broken? In what ways? Okay, could have an infinite asymptote, which it calls a break. What else? Jump or gap. Okay. All right. Removable. Sure. Okay. Smooth. What's the opposite of smooth? Okay. Rough. Yeah. Jagged. Okay. Maybe. Okay, so if you encounter a corner, something that is jagged, okay, or not a smooth corner, an abrupt change, okay, that would not have a well-defined slope. That's what happened the last time. We were a cubic connected to a linear. A cubic connected to a linear is an abrupt change, okay, and that is not a smooth transition from one to the other, and so that is often an indication of non-differentiability. Yeah?
Are like most piecewise functions or not?
Most of them are. Occasionally, you get one that does have a smooth transition, and you can prove that when you check the derivative, but most of them are, yeah. Even if they're continuous, they might be connected, but not differentiable. Okay, great. Okay, so the places where things aren't differentiable, there's kind of 4 big ones to look at. All right, the first one are the discontinuities you just listed. Okay, the discontinuities that you just listed. That would be non-differentiable. Okay? Number 2. Graphs that have a corner. There's a classic graph that has a corner. Can you think of what that is? An absolute value. That's classic. But the one we just encountered was the cubic connected to the linear that had a corner too. That's not differentiable because it's not a smooth transition from one to the other. Okay? We have something called a cusp. All right? A cusp, I think of it kind of like a wave. It's like where the one side of the graph is coming up like this and the other side of the graph is going down like that. That would be considered a cusp. So it's the peak of 2 waves. Or, you know, you could. Okay, that's a continuous function. It's a function. It passes a vertical line test. It's continuous. There's no gaps or jumps or discontinuities. But it's not differentiable because you have all these cusps. Okay, and every cusp represents an abrupt change from one kind of slope to the other. Because coming up one side of the cusp, what kind of slope do you have? Positive. And then going down the other side of the cusp? Negative. It's an abrupt change from one to the other. Okay, and the last one are vertical tangents. Okay, a vertical tangent is a point at which the graph for just a moment is completely vertical. Okay, it doesn't last for very long. Okay, but an example would be a cube root. A cube root function goes like this and then goes through the origin and then heads out like that. The moment it crosses through the origin, it was instantaneously vertical. Okay, I could maybe exaggerate my graph and draw it a little bit better if I went like this and then like this and then like that. Okay, like at an instantaneous moment, it was vertical, and we call that not differentiable either. Other graph like that would be the inverse of tangent is drawn like that as well, but the cube root is a famous vertical tangent function. Now, hear me, a vertical tangent is not the same thing as a vertical asymptote. Just like yesterday, a horizontal tangent is not the same thing as a horizontal asymptote. These are vertical tangents. If you identify and visibly see any of those with your naked eye, automatically non-differentiable. And you can identify and just claim it. I see, it's a cusp. I see the cusp. Okay, yeah.
Does that mean that horizontal tangents are differentiable?
Horizontal tangents are. Vertical tangents aren't. Okay, so here's a classic corner. Okay, I can visibly identify, yep, corner, continuous, yes, differentiable, no, but you might need to prove it. Okay, and a proof is not, well, I just looked at it and I saw a corner. That doesn't work for a proof. Okay, a proof needs to be algebraic and mathematical in nature. So you're going to have to split this absolute value into its two pieces. I've showed you how to do this before. Okay, so let's look at this algebraically. How do I split up an absolute value into two different pieces? Okay, negative x, so it's a slope that's going down when x is less than 0. Positive x when x is greater than. Doesn't matter where you put the equal to. Okay, either one. I could put the equal to, on, not on both, but I could put my equal to in either one. It doesn't matter. Okay, so if we're checking, the proof would be checking continuity first and differentiability second. So let's check continuity, which means limit x approaching 0 left of negative x. Is that equal to limit x approaching 0 right of positive x? And is that equal to f of 0? So we put the little question mark, and we're investigating, and we're practicing an easy one so that we can just get our process down. So we're investigating the continuity. And in this case, 0 does equal 0, which equals 0, and all three of those are equal, therefore continuous, yes. So then you move on to prove the point of differentiability, which you know visibly, you can tell it's not going to be differentiable, but we want to prove it. And so we're going to check the limit approaching 0 minus of the derivative. And what's the derivative of the left piece? Negative 1. And then question mark, is that equal to the limit approaching the right of the derivative of the positive piece? And the derivative of that is positive 1. And so those are constants. Negative 1 is not equal to positive 1. So my differentiability is proven not to be true. So continuity, yes. Differentiability, no. Because again, it's a hard transition. It's an abrupt transition. Okay, you're like, I have a slope negative 1, negative 1, negative 1, negative 1, negative 1, negative 1, negative 1. And then, boop, I switch to, there's not a gradual change. It's an abrupt, complete change from one to the other. So we say, if you're asked, what's the point of non-differentiability? In other words, where's the one place where the differentiability changes? And you say at 0. Okay, 0 is the point of non-differentiability. Oh, whoops. I think I intended to do all of that work right there. Okay, you guys have notability. You can copy and paste and slide your stuff down if you want. We checked the left-hand limit, we checked the right-hand limit, we checked it all, sorry. All right, so we don't have to do slide 9 because we did all of our work on slide 8. Okay, here's a cusp. There's another example of a cusp. Okay, so this is a sample of one. It's x to the 2/3 is the function. Okay, and again, let me see, make sure I didn't. Okay, we'll do all our work here again. We'll check our continuity. I'll do it in black. Okay, our continuity, the limit approaching, and 0 is my target point because it's clearly where the cusp is happening. So I want to check 0 from the left of x to the 2/3. I want to check 0 to the right of x to the 2/3. There is no different equation to use because this is not a piecewise function. And I'll check f of 0 itself. And again, these are all zeros. So continuity, yes. Then the question of differentiability. All right, am I going too fast? Okay, differentiability. Let's check the limit as x approaches 0 from the left, and now we want to check the derivative. All right, Stephen, you want to give me the derivative?
2/3 times x to the negative 1/3.
2/3 times x to the, okay, it's not negative anymore because it is in the denominator already. Okay, or I'm not sure, maybe I just misunderstood what you were saying. Were you saying 2/3 x to the negative 1/3 like that, or were you meaning?
Like that, yeah.
Okay, so we don't want to leave a negative. We never want to have a negative in our answer. So where should that negative 1/3 go? Okay, so let's write it that way. Okay, so we want 2/3x to the 1/3. And then we're checking, is that equivalent or equal to the limit on the right, and the derivative is the same. Okay, so when I plug in 0 minus, okay, what do I get? Okay, I get 2/3 times the cube root of 0 minus. And the cube root of 0 minus is also 0 minus. And 2/3 times 0 minus is going to give me a version of infinity. What version of infinity is that going to be? Negative. Okay, so this is negative infinity. On the other side, when I plug in 0 plus, I'm also going to get a version of infinity, but what version do I get? Positive infinity, okay? Those are not equal. Okay, what if they both turned out to be negative infinity?
Then it would be oh, because two infinities are never
Two infinities are never equal to each other, okay? There's no way to say that negative infinity is the same as this negative infinity, or this positive infinity is the same as that positive infinity. Okay, two infinities are never equal to each other because there's no way to tell what level of infinity you're at if you can think about different levels. But here, these are clearly different because one's negative and one's positive, yeah.
What is that? I guess what does it mean by like negative infinity?
As a slope, it means it's going down it's decreasing at a rate that's practically vertical. Okay, so yeah, it is approaching to this point. Its slope, if we could zoom in on this far enough, its slope is approaching the point, not getting there, but approaching the point where it's almost practically vertical. And on the other side, it's approaching the point where it's almost, okay, like if you saw Top Gun, it's like they're approaching, right? They're going into, they say I'm going vertical, right? But if they actually got vertical, I think that the way the physics would work out is that their engine, if they actually truly were vertical, they may end up going into free fall, right? Isn't that? I think that's what the physics on it.
What are we talking about, cars?
What? Top Gun. Sorry, planes.
That would really come
Big honest.
All right, here's another one. Okay, so I already told you about this one. Here's the cube root here. Okay, again, we can prove the continuity pretty easily because the left and the right-hand limits are all 0. Okay, so we can kind of fly through that the continuity approaching 0 from the left of the cube root of x is equal to the continuity, to the limit value on the right of the cube root of x, which is all equal to f of 0. So as I'm investigating those, the equality is proved. So you can kind of, we're getting in the rhythm of how these go. All right, then we want to check the differentiability here. So I need the derivative. All right, so Nick, the derivative of the cube root. I can see the wheels turning in his head. He's converting it into a fraction in his head. They're almost there. All right, what would be the ease, if you're thinking about a cube root, what do you want to do to that cube root? Like we had on the worksheet we just did. You want to think of it as x to the 1/3. I think it's a lot easier than to think about that so that you can move the 1/3 to the front and then actually subtract. All right, so Nick, does that give you enough to get going? So what would I end up with? And we can do all the changing later. Let's just get a version of it first.
1/3
Okay, 1/3 x to the negative 2/3. Okay, so now let's make sure we don't have a negative exponent. So what would that end up looking like?
1/3 3
Okay, good. All right, so we're going to rewrite that as 1/3 x to the 2/3. And sorry, I'm realizing I wrote plus instead of minus right there. All right, and then we want to investigate, is that the same on both sides? 1/3 x to the 2/3. Write that a little bit. 2/3. Okay. We're going to get a version of infinity for both of them. Okay, what version of infinity do we end up with? Okay, this is really interesting mathematically. When I put 0 minus into this equation right here, all right, if I put 0 minus into here and I've got x to the 2/3, okay, what does the 2 tell me to do? Square it. And what does the 3 tell me to do? Cube root it. What should you do first?
Square.
Oh no, always do the root first, because with the root, no matter what you plug in, always do the root first because it's going to make the number smaller, which will eventually make your squaring bigger as opposed to making it really big. And so I would recommend, it's not wrong to do it either way, but if you're using other numbers, always do the root first. All right, so we put 0 minus in, and we'll do the root first. What's the cube root of 0 minus? Still 0 minus, we just saw it. And then what do you do with that 0 minus?
Square it.
Square it. What's the square of 0 minus?
0 plus.
Oh, 0 plus. So now we've got 1/3 times 0 plus.
Because remember, a negative times a negative is a positive.
Yeah, 0 minus is a negative number. So what kind of infinity we end up with? Okay, positive infinity. Okay. The other side is a little clearer because it's already in a positive. We end up with positive infinity. However, those two positive infinities are not equal to each other. Okay.
Big brain calculus.
Yeah. All right, so not differentiable.
So I have a question when you come to like the fraction part. When you like write it out in like its radical form, it's like the cube root of x squared. So when it's like that, wouldn't you have to do the x squared first?
Well, you could write, okay, Rose has a question. She's saying, is x to the 2/3, is it the cube root of x squared, or is it the cube root of x squared?
That's not what I'm saying. I'm asking, why are we doing the
Well, my argument
part
is
first?
it doesn't matter. Either one of those is equal. Those are the same.
What?
Okay? Yes, those are the same. And my argument is, I think mathematically, it's easier to, you do the thing inside first, right? So do you want to square? Okay, so let me give you an example. Okay, so let's say we'll do 8 to the 2/3. Okay, so is that the cube root of 8 squared, or is it the cube root of 8 quantity squared? Okay, so what's easier I forgot my cube. Okay. Okay? Now, these are fairly small numbers, but in this one, you're going to do 8 squared, which gets you 64, and then figuring out the cube root of 64. Okay, well, I mean, that's not horrible. Or we can do the cube root of 8, which is 2, square it, you also get 4. So you get 4 either way, but then you start getting to numbers that are bigger. Okay, so suppose you had 125 to the 2/3, okay? Do you want to do the cube root of 125 squared, or would you rather do the cube root of 125 and the quantity squared? Okay, so what would you rather do? So are you going to square 125? And I'm just talking mental math here. I mean, if you had a calculator, right? But I think it's easier to do the cube root of 125, which is 5, and then square that and get 25. As opposed to doing this, squaring that, and then having to figure out what that number is and the cube root working out to be 25. Okay? So
That's crazy.
I'm just
They're
saying
the same thing though.
they are the same thing. All right, we're almost done.
Question.
Yes.
So what if you had like a binomial and you had like x plus
No.
1 to the 2/3?
Mm-hmm.
What would you do then?
Well, that's an algebraic as opposed to an arithmetic, right? Arithmetic is dealing with just numbers, and now you're talking algebra because you've added a letter
Yeah.
to it. I would put my square, and then I'd do my square first,
So you square it
and then cube root the whole thing.
cube root the whole.
Right, but if I was working with numbers and I was plugging a number into
Yeah,
that,
yeah.
I would do the cube root first. Okay, so either, I'm saying there's always lots of different ways legally to do things, but there's usually an optimal way that makes it easier for you to do like the mental math on it. Okay. All right. Okay, a good way to think of differentiable functions is that they are what we call locally linear. Okay, a locally linear function means it's made up of tiny little lines. Teeny, like local, like tiny little line segments. This is how the Greeks thought of it. They didn't think of it as a circle. What did they think of it as? A polygon with like infinitely many sides. It was, and the smaller the side, the smoother the shape it became. And so this is the same thing. Okay, a function is made up of tiny little pieces. The more pieces you have, the smoother the function gets. Okay? All right, in terms of now that we have graphing calculators, we can zoom in and zoom out with a lot more ease than Newton and Leibniz could. They couldn't do that. But we can take a calculator and we could zoom in and zoom in and zoom in and zoom in, and eventually it'll just look like it's a line. Any function you can zoom in on all the way will eventually look like a line because you're so close to it. Okay, so here's an example. I took a couple little screenshots. A function that starts out all squiggly. If you zoom in on a particular piece of it, so I zoomed in on this particular piece right here, okay, which took me down to here. And then I zoomed in on just a piece of it, which took me to there. And now it looks like it's pretty much a straight line. So what if you went the other way? If you only had this part of it, would you have any idea what the rest of the function looked like? Okay, it's almost impossible to go back and to know. And even if I gave you this much of it, what might you think it was? Parabola, or maybe a piece of a sine wave, or who knows? Okay, and then how would you even know that it looked like that? Okay, so however, this is if you zoomed in on the vertex of a absolute value. Okay, just the vertex part, the corner. You zoomed in on the corner, and you zoomed in again on the corner, and you zoomed in on the corner. What's it always going to look like?
Absolute value.
It's going to look like a corner. No matter how far you zoom in, you could never make that corner straight. Okay, so that's a visual idea of differentiability. That of a differentiable function that has no corners, no cusps, no vertical tangents, no points of discontinuity. Those 4 things that no matter what piece of section you just chose to zoom in on, it would eventually look like a line. Whereas a non-differentiable function, the point where it's non-differentiable, if you zoom in on that, it will continue to, a cusp will always be a cusp. A corner will always be a corner. It will never look like a line. Okay, we call that local linearity. Local meaning a small region that you're zooming in, linearity meaning it looks like a line to you. All right, so here's that. If we zoomed in on this piece, that corner will always look like a corner no matter how close we get to it. All right, so here's our takeaway, and this is, Catherine, what I alluded to earlier. If f is differentiable, then it is also continuous. The order of the presentation of those two facts go hand in hand. If you know it's differentiable, it only could have come from a continuous function. But the converse is not true. If x is continuous, then f might also be, could also be, maybe also be differentiable, but there is no guarantee. So the classic, all you got to do is say, point to an absolute value and go there. Okay, it's continuous, but it's not differentiable. Point to a cube root. There, continuous, not differentiable. You can come up with lots of different examples. Okay, if it's not continuous at all, it's for sure not differentiable. That's impossible. Okay. All right. Any other questions on that? Yeah.
What are some examples of differentiable functions?
Anything that doesn't have
Straight line.
a corner, a cusp, or a vertical tangent. So
Just like a
line
line.
for sure. Okay, sine graph,
Oh,
parabola. Okay, doesn't have a corner,
Am I thinking too big?
doesn't have a cusp, doesn't have a vertical tangent.
So
Isn't
parabolas.
it like on one side it's going
Ooh,
Isn't the slope
Set-
like infinitely slightly bigger or smaller on like a parabola or no?
Yeah.
all right. What's the equation of that parabola? Negative x squared. All right, let's check it.
Oh no.
Okay, so negative x squared, and the limit on the right of negative x squared, and then the function itself of negative x function at 0. Okay, so we're assuming that that's the origin right there. And so the values of all of those are 0. Okay, so it's continuous. We know parabolas are continuous. Okay, is it differentiable? All right, what is the derivative of negative x squared? Negative 2x. Okay, what is the derivative? Okay, I said that. Negative 2x. All right, so if we plug 0 minus into that, and we put question marks here because we're investigating. All right, what is the value if I plug in 0 minus times negative 2? 0 what? 0 plus. Okay, if I plug in 0 plus into negative 2x, what do I get? 0 minus. Is that equal? Yes, we talked about this. They are both, these are limits. Okay, am I saying will it ever get to 0? No, but what are they both approaching? They're both approaching 0. They're both approaching the same integer value. Okay, it's approaching the same slope. Doesn't have to actually get to the same slope. These are limits. They are approaching the same slope. So these values, the plus and minuses, the little plus and minuses don't matter. With infinity, the big plus and the big minus, those matter 100%. But yeah, as long as you're approaching the same integer value, just like with limits.
So what does this look like in the real world? I know like yes, please. But like I'm like everything else, I know how to do these things.
Yes.
But like I can't picture it in a real world scenario.
Okay. So let me see. Rewind in your mind 3 years ago.
Oh no.
Okay? All right. Just before COVID, right? Okay? We were starting to hear about COVID. Just a little bit. Okay? And the cases of COVID are starting to climb, and then all of a sudden the cases of COVID start to climb. And then what did they call it? Like when a spike, right? All of a sudden we hit this. Okay? That's hitting a vertical tangent. Okay? We're going like this. And I don't know if you're old, even, if you were aware enough, but all the politicians and stuff are starting to talk about, we need to flatten the curve. That's what they were talking about, okay? We need to wear your mask, and then, socially distance. This was all at the beginning, before we had vaccines, flatten the curve. That was the goal, because they needed to break that vertical tangent. We could not, as a society, sustain that vertical tangent anymore. So what were we going to do? We were going to wipe down your groceries when you come in from the grocery store. Do you remember that? Okay, yeah. But that was the goal. They were trying to flatten the curve. In other words, they were trying to change the slope so that we would go like this instead. Okay? So in the terms of mathematics, mathematicians are all like, ooh, point of non-differentiability. That's the point where the slope changes. And they were making models, and they were making equations, and they were trying to predict, when is this going to happen? When is the slope when is the breaking point? Okay? And so, the people who were, they call them, Emily Decker is this. I forget. It's a type of mathematician that works on, it's part stats, and so they were working on, trying to come up with these models. And, it was all guessing, because we'd never encountered anything like that before. But that would be a point. We started to hear the language of, like, flattening the curve and things like that spike that we were talking about. So there's one example of where that comes into play. Okay? All right, 15 minutes. Why don't you get started on 2-2? I've picked them. They're on 2 different pages, so make sure you're on the right page, doing the right assignments. Okay. Yeah. Let me make one announcement first. One other thing I wanted to pass on to you. One of my former AP students, Mr. Taminga's daughter, Catherine, she was in the class of 2020, so that was the year of COVID. She's a junior in college locally, and she reached out to me, and she's like, hey, I just wanted to let you know I'm in the area, and if any of your AP Calc students want a tutor or need help, I'm available as a resource. So if you are feeling like I could use another person to, talk things through, or get a boost, or get help maybe once a week or twice a week, reach out to me, and I'll pass on Catherine's contact information to you. You guys would have probably been freshmen when she was a senior, I think. So if you want that, let me know. Okay. You remember that freshman year? We're like, yes, no more. It's Friday the 13th. It was Friday the 13th.
Oh yeah.
It was. It was Friday the 13th.
And I was in 6th grade.
Yeah.
What do we write here?
That the corner will always be a corner. Okay, that little spot will always be a corner. You get closer and closer and closer to it, it's always going to be the same. It's always going to be a corner. Not ever going to be a line, straight line. Okay?
Like, that was literally the most depressing time of my life.